Now that we've spent some time thinking about mafic and felsic minerals, let's consider how mineral composition has an impact on volcanic eruption styles. First, I need to introduce you to Bowen's reaction series. This is named for Dr. Bowen, who first put together this model of silicate minerals that crystallize out of a melt. And this melt sequence is dependent primarily on temperature and secondarily on composition. You'll notice in this diagram on the left-hand side, we've got a range of temperatures going from high at the top to low towards the bottom. In the center of the diagram, we have a list of minerals, and they're sort of in these blob shapes and organized on the left as a discontinuous series of crystallization, and on the right as a continuous series of crystallization. On the right side of the diagram is a list of igneous rock compositions ranging from ultramafic at the top down to felsic at the bottom. So let's make connections across this diagram. At the top of the diagram are the first silicate minerals to crystallize. These are the minerals that are most stable at high temperatures. As we move down the diagram towards the lower temperatures, towards the last minerals to crystallize, these minerals are stable in solid form at the lowest temperatures. What this means in terms of crystallizing a magma is that minerals are going to form in a definite and predictable order within that magma melt. And we're going to start with the minerals stable at the highest temperatures crystallizing first, removing that composition from the remaining melt and working down towards the minerals stable at lower temperatures. The two sides of this diagram include the discontinuous series and the continuous series. And this is referring to mineral families, or mineral orphans, if you will. The mineral family represented on the right-hand side is that of the feldspars. So when we looked at minerals and element substitution, I used feldspars as an example, with potassium, sodium, and calcium ions interchanging within the feldspar crystal matrix. In terms of the Bowen's reaction series, the feldspars form a continuous series of crystallization, which simply means that at highest temperatures, calcium, which is a very large ion, will fit easily into the crystal lattice. And as the temperatures reduce over time, sodium will substitute in more frequently. And then as we get cooler still, we get potassium fitting in there. So it's continuous because we have a single mineral that is represented with only this one ion exchange as temperatures get cooler. The discontinuous series are completely different minerals altogether. From olivine to pyroxene to amphiboles to micas, these discontinuous minerals all have totally different crystal structures. Olivines are single tetrahedra. When we get to the pyroxenes and amphiboles, we've got single and double chains. And when we get to the micas, then we have these sheeted structures. So they have very different crystal forms. If we look at the right-hand side of the diagram with the rock compositions, what you can see here are representations of what minerals we're actually going to see within those rock types. So the ultramafic rocks are going to be composed of olivine, pyroxene, calcium-rich feldspar, whereas when we get down to intermediate rocks, we'll be seeing sodium-rich feldspar mixed with amphibole and biotite. As we get to the felsic rocks, then we see a prevalence of quartz, potassium feldspar, and the muscovite mica. We're not going to see ever in a single rock olivine and quartz because those form at such vastly different temperatures. Now, this does actually connect to volcanoes, and that has a lot to do with this factor of temperature. And it also has to do with the fact that we're not going to see felsic compositions in the same rock as mafic compositions. So let's take a look at two types of volcanoes, beginning with shield volcanoes. Shield volcanoes are broad, dome-shaped, massive volcanoes. They are by far the biggest volcano type that we have on our planet. And Olympus Mons, not on our planet, but on Mars, is a shield volcano as well. And it is significantly larger than every volcano here on Earth. These volcanoes, relatively from width to height, have an interesting ratio. That is, they are significantly broader than they are tall. And the reason for this broad dome shape has a lot to do with the composition of the volcano. Shield volcanoes are mafic in composition. The mafic composition for shield volcanoes is really important because the low quantity of silica in a mafic composition melt directly relates to the viscosity of the magma. The higher the amount of silica, the higher the viscosity. So shield volcanoes, being made of lava flows that are low in silica, have low viscosity. This means that they flow really easily. And as they flow really easily, they're going to spread over great distances. And instead of piling up high, they're going to spread out wide. And this is why we get these broad dome-shaped volcanoes. In addition to the low silica composition contributing to a low viscosity melt, they're also produced from these mafic minerals, which are more stable at higher temperatures. And higher temperatures tend to result in lower viscosity melts. You think about ice cream and its temperature relationship, the higher the temperature, the meltier that ice cream is going to be. This is a photograph of lava from Kilauea in Hawaii. And this is a type of lava that we call pahoehoe or ropey. And you can see in this photo just how flowy the lava appears to be. And this is a broad view of Mauna Loa, another shield volcano in the volcanic island chain of Hawaii. And you can see clearly here its broad dome shape. And it is quite massive indeed. Now let's switch gears. Recalling Bowen's reaction series, we just looked at examples of shield volcanoes, which are primarily mafic, which means they're primarily made of basalt, composed of olivine, pyroxene, amphibole, and calcium-rich and some sodium-rich feldspars. Now we're going to move down into a cooler temperature magma, into an intermediate and more felsic composition melt. These types of volcanoes are called composite or stratovolcanoes. In this diagram, what you can see are a series of layers. When you think of the word strato in the context of stratigraphy, which referred to rock layers, stratovolcanoes made of layers of lava flows make sense. We also call them composite volcanoes because they are composed of two main layering components. That is lava and pyroclastic material. The pyroclastic material is material that has exploded out, and it might be fragments of rock and lots of ash and any ratio of those two things, whereas the lava flow is directly molten material flowing on the surface. So this stratigraphy of interlayered pyroclastics or exploded material with lava flow makes up the stratigraphy of a composite or a stratovolcano. An example of this is Mount Pinatubo in the Philippines. In this photograph, you can't really see where the volcano is, but you can see where its eruption is. And you can also see where the pyroclastic or exploded material would come from. Mount Pinatubo famously erupted in 1991, and this is a photograph from that time. To have an example of what it might have looked like prior to the eruption, I was unable to find a photo quickly, we can look at a neighboring volcano called Mount Mayon. We can also look at what Pinatubo looked like from overhead before the eruption, which we can see here. So it's not quite as pointy as our example, but you can see it has a peak. Now after the eruption, that same angle of view, you can see just how much material was lost. The estimate is over 12 cubic kilometers of material blew off. I'm sure you can think of other examples of explosive volcanoes from the recent history, and maybe even from more ancient history, like the time of the Romans. Pinatubo has a famous photograph accompanying it, and that is this one, with these volcanologists racing away from the pyroclastic ash flow rapidly coming at them. To summarize with just these two examples of volcano styles, shield and stratovolcano, let's look at the factors that impact just how explosive volcanic eruptions can be. I've really emphasized temperature and composition. That is, the hotter the lava, the runnier it will be. And the more silica contained within the melt, the stickier it will be, the more viscous it will be. But there are two other factors that are also going to contribute to how explosive an eruption is. One of these is dissolved gases, and another one directly related to that is pressure. A good way to visualize this is to think about a can or a bottle of soda. If you open a bottle of soda, you can hear the gases being released. The fizzier the soda, the more gases get released, and the same thing goes with a volcanic eruption. The more dissolved gases are contained within the melt, the more likely it is to have an explosive eruption. And we can contain the gases by containing them with a lid, as it were. So if the volcano is sealed on top, that is, the pressure of those gases is allowed to build up inside because there isn't an opening that's readily letting gases out, then the more gases will build up, the more pressure will build up, and the more violent the eruption will be when it finally breaks through the crust. Now that sentence, breaking through the crust, leads us to the other thing that needs to be considered, which is the type of crust, the type of lithosphere, as well as its thickness. So, for example, Mauna Loa in Hawaii, this is oceanic lithosphere. An oceanic crust is made of mafic material. It's made of basaltic material. So naturally, when that melts, it's going to be richer in iron and magnesium and be more mafic in composition because that is what it's made of. If you melt continental crust, that tends to be more felsic or intermediate in composition. So naturally, that's going to control that composition. But what if the lithosphere is changing over time? If we were to follow the pathway of Yellowstone, which is a hotspot volcano in the center of the North American crust, it used to be west. And its volcanic eruptions over time have changed from mafic to felsic. That change has correlated with how much continental crust has been melting into that hotspot source over the last couple of million of years. In contrast, the subduction zone along the west coast of North and South America, we've got oceanic crust sinking beneath continental crust. So those volcanoes are more intermediate to felsic in composition. Finally, the thickness of the crust has a huge role to play. If there's a lot of crust in the way, then you might not get a volcanic eruption at all. Or you might get volcanic eruptions that are quite explosive because there's a thick cap that the gases and melt have to break through in order to finally erupt. Now let's translate that to a fun fact to end this lecture. And that is, what is the tallest mountain on Earth? Is it a mountain or is it a volcano? Everyone automatically thinks that Mount Everest is the tallest mountain on Earth. And it is very tall, relative to its place above sea level at nearly 9,000 meters tall. It is got the highest altitude above mean sea level. Mauna Kea in Hawaii, by contrast, starts well below sea level, starts down on the ocean floor, and that mountain is significantly taller than Mount Everest. So Mauna Kea as a volcano is over 10,000 meters tall, making it over a full 1,000 meters or a full kilometer taller from base to tip than Mount Everest. But the mountain that's actually the closest to the sun is Mount Chimborazo, which happens to be on a subduction zone. So we have three totally different mountain building types of mountains featured here in this comparison. But Mount Chimborazo, which is near the equator, is situated on the widest part of the Earth. The Earth is an oblate spheroid, not a sphere. So the central part, the equatorial part of our planet, is actually significantly wider. It's the oval part of the rugby ball shape of our planet than the polar regions. So by its location on Earth, Mount Chimborazo is actually quite a bit closer to the sun or further from the core of our Earth than either of those two. So there you have it. Mount Everest, formed by continental-continental collision. Mount Chimborazo, formed at a subduction zone, and Mauna Kea formed at a hotspot. Which one do you think is the highest mountain on Earth?